Okay, hello everyone. Thank you for coming to this talk. Just earlier today, Simon Ritter from Azul Systems had a talk about the new stuff in JDK9. And just before my session, Steve Poole from IBM also had a session on basically what are the main security vulnerabilities. And he presented some nice tips on what we as Java developers need to consider when we have to deal with security vulnerabilities in the Java platform. And my session basically provides an extension of those two talks. I speak mostly about what are the new security enhancements in Java 9. I'll show you some examples of them in practice. And also I'll discuss a bit how does the new module system in Java 9 impact the security of the platform. How many of you are aware of the new module system in Java 9? Okay, half of the people. So just before we start with this session, a few short words about me. My name is Martin. I'm working through a company called Coffee Consulting. It's a one-man show company. I'm doing mostly Java consultancy. And I'm also one of the guys who helps organize the events of the Bulgarian Java user group, where we also have our own community conference called JPrime, which runs end of May. I'm also a very big OpenJDK enthusiast. And just like 2 years ago, I wrote a book on RabbitMQ. So if you're interested in enterprise integration patterns or messaging solutions, we can discuss anything related to RabbitMQ or other solutions in particular. And I tweet mostly about Java, so you can follow me on Twitter. So in this session, I would like to present you what are the new security enhancements in Java 9. Some of you may think these are quite specific enhancements added to Java 9. However, as I'll try to show you, these are really some interesting enhancements added to the platform. But just before we dive into the talk, I want to discuss briefly how does the new module system in Java 9 impact the security of the platform. As most of you know, the new module system in Java 9 allows you to split your application in so-called modules. They contain the so-called module info.java file that specifies the metadata for your modules. And also you have a new tool called JLink that allows you to build a custom JDK image that contains just a smaller subset of modules from the JDK. This has two major implications in terms of security. The first one is that since you now have the possibility to build a smaller JDK using the JDK9 JLink tool, this effectively improves the security of your application, since basically you get rid of many classes that you don't need in the JDK. And the other side of the coin in terms of the module system is that you have another layer of encapsulation provided by Project Jigsaw, and that's the ability to specify exported and imported packages as part of your module definitions. This effectively also increases the security of your application, as you basically sandbox the application into a module and you just specify which packages are visible to the outside world. So these are the two main implications of the Jigsaw module system. It effectively improves the security of the platform. Another interesting thing about this is that it aligns well with the existing security sandbox model in the Java platform, which makes use of security manager, access controller classes, and the default permissioning system that allows you to specify permissions in the so-called security.policy file, which resides in the JDK installation. The new module system allows you to specify security permissions for Java modules in the same way as you do for jar files, class files, and so on, in the syntax of the security.policy file. One new addition to the format of that file is the JRT extension, which allows you to specify that you apply permissions for a Jigsaw module. And that's the main addition. So basically, the Jigsaw module system aligns very well with the security sandbox model in the JDK platform, which is out there since version 1.2 of the JDK. As you might guess, this is a very old model that's been adopted in the JDK, but this model applies up until JDK 9 and beyond. So in this session, first I'll start by showing you what's the current state of TLS support in JDK. And basically, I would like to do a recap of how does the JDK provide support for the Transport Layer Security protocol, which is the successor of the SSL series of protocols. Then I'll discuss a new enhancement, which is provided by the support for the DTLS protocol in JDK 9. Or DTLS is effectively the TLS protocol over an unreliable protocol such as UDP. Then I'll show you how you can use the TLS ALPN extension, which is another interesting addition to the TLS support in JDK 9, and the ALPN extension provides you with the capability to negotiate the application protocol during the TLS handshake process that effectively establishes the TLS communication between the parties. And at the end, we'll review what are the rest of the security enhancements introduced in JDK 9. As some of you know, JDK 9 is already not supported, meaning that its support is over, but this doesn't mean that the features that we will see now will not be supported in JDK 10 and the long-term support release, which would be JDK 11. So let's first revisit what is the state of TLS in JDK before Java 9. So up until Java 9, the Java platform supports different versions of the TLS specification. The latest one of them is version 1.2. And currently there is a version 1.3 of the TLS specification ongoing. Just a few weeks ago, the Oracle security team announced that it started implementing the new features from the TLS 1.3 specification. So we might expect that in Java 11 or Java 12, we'll see new enhancements in TLS coming. And typically, as you know, TLS is used to secure most type of internet traffic and also the traffic that flows within the premises of your company. Another interesting use case of TLS is that it can be used to implement the so-called SSL VPNs that can be used to establish secure communication to your company's network. So you may think that TLS is the de facto standard protocol that allows you to secure communication traffic between endpoints. And just before we discuss how does the JDK support TLS, we need to understand what's the TLS handshake process. This is in fact the first step that kicks in before any TLS communication can happen. So at the first step, the client proposes the TLS version and the supported cryptographic chiffres by that client. The server gets that request, and based on the information provided by the client, says, okay, we can negotiate that we'll use that version of TLS along with those cryptographic chiffres, and I'm also sending you my public certificate that contains my public key. At that point, at step 3, the client takes the public certificate from the server and may do certificate validation. Certificate validation is done against a certificate authority, whereby the client may use the information provided by the so-called CA certs file, which stores information about which certificate authorities are trusted by the client. This file resides by default in the installation of the JDK. So at the third step, the client may do certificate validation. It can do that using things like the OCSP protocol or certificate revocation lists. These are the two main ways a client can do certificate validation. When the client does this and validates the certificate provided by the server, at step 4, it may optionally send its own public certificate to the server. And this is required so that the client and the server may establish bidirectional communication between each other. In many scenarios, you might only need the public certificate of the server, but in some cases, you might also need to provide your own public certificate to the server. And at that point, when the client does this, it uses the public certificate of the server at step 5 to generate the so-called shared secret key. And that shared secret key, in fact, is used to establish the secure communication between the client and the server. So when the client generates the shared secret key and sends it back to the server and the client exchange 2 additional messages, which are client finished and server finished. And at that point, TLS communication can start happening. So it's essential to understand this process because many of the enhancements that we'll see now and that will come into future versions of the JDK rely upon this process. Now, in terms of Java, support for TLS is provided in terms of the so-called JSSE API or the Java Secure Socket Extension API. You may think of JSSE as an extension of the standard Java sockets as you know them, but in addition to that, the JSSE API also provides a non-blocking mode of operation. And by default, the JDK provides a default implementation of this API, which is provided by the so-called Sun JSSE provider. Most of the security APIs in the JDK are provider-based, meaning that they provide some API without concrete implementation of the algorithms. And in the JDK, we have some series of default implementations of those provider APIs. And also we have some third-party libraries that provide implementation of those providers. One of those libraries that some of you might have used is called Bouncy Castle. It provides a lot of implementations of various cryptographic algorithms and so on. So in terms of Java, the default implementation is provided by the Sun JSSE provider. Also, core classes are part of the javax.net and javax.net.ssl packages. As we mentioned, it provides two modes of operation. One is the blocking mode of operation, which is similar to how we would create standard socket communication. And also there is a convenient class which might be used if you need to establish HTTPS communication between endpoints, which is provided by the JSSE API. It's called javax.net.ssl.https URL connection. It effectively simplifies the way you establish communication over the HTTPS protocol. Now, to give you some more insights, let's look into the JSSE blocking mode of operation. Its API is provided by the javax.net SSL socket class. As we already mentioned, it can be used in a similar fashion as standard Java sockets. However, the essential thing here is at what point do you trigger the TLS handshake process when you establish communication between the client and the server. One way you can do that is by explicitly calling the start handshake method on the SSL socket instance that you have created. This kicks in the SSL handshake process. Or behind the scenes, if you try to get the current SSL session by calling the getSession method from the SSL socket, this also triggers the TLS handshake process if it isn't being triggered already. And the last thing that you may consider when you need to know how the TLS process is triggered is by trying to read or write to the socket. When you try to read or write to a TLS socket, if the handshake process isn't established, it is established behind the scenes for you. So these are the three main ways you can establish the TLS handshake process. And this is a more concrete example. This is an example of a JSSE server. The first two things, you specify two properties. The first one points to the key store on the server, which stores the public certificate of the server. And as you can see, this public certificate, this key store provided by the server has an extension which is PFX. This is one of the new enhancements in Java 9, and basically in Java 9 we now have by default PKCS12 Keystores, which have this extension. So basically we specify the public key store for the server that stores the public certificate. We may specify some password for that key store. Then we use a factory called SSL Server Socket Factory. This factory basically is used to create, as you might guess, SSL server sockets. We create one SSL server socket at port 4444, and then we call the accept method to get some, to wait for some information to be received by the server. At this step, you might guess that this operation is blocking. So that's why we say this API is blocking. We wait for some information to become available on the server. It works in a very similar way as standard Java sockets do. So when we get some information on the server, we get an input stream from the server socket. We read the information, and at the end, we make sure that we close the input stream along with the server socket. And this is how a very simple SSL client looks like. It has a very similar structure as an SSL server. On the first two lines, I set a trust store for the client. A trust store basically stores information about all the trusted certificate authorities that are used by the client to validate the public certificate of the server. Then I may specify some password for that trust store. And then I use another factory, which is called SSL Socket Factory, to create SSL client sockets. Again, I create a client socket on port 4444. I send some information to the server, which is some message called hi server. Then I get an input stream for the client socket, and I read some information back from the SSL server. And at the end, I make sure that I close the input stream and the client socket. As you might see in those two cases, I just create a request-reply communication, very simple, between the client and the server. And in JSSE, we have a much more complex way of operation, which is the non-blocking mode of operation. It's much less known to the Java community, and it's provided by the javax.net.ssl engine class. The SSL engine API is much more complex to use, and in short, to understand how it works, if we look at the diagram on the right side, first, if we want to send some data over to the network, we use the wrap method to send that data to a so-called application byte buffer. The application byte buffer resides on the application side, and when it gets that information from the SSL engine, it sends it over to the network by writing it to the so-called network byte buffers. When we need to read some information asynchronously, we use the unwrap method to read that information. And when we call the unwrap method, we read that information if it's available again from the network byte buffers, from where we write it to the application byte buffers. And from those application byte buffers, we get that information and use it in our application. One similarity between the non-blocking and blocking mode of operation is the way you trigger the SSL handshake process. Again, the SSL engine API provides you with the so-called begin handshake method, which allows you to trigger the SSL handshake process. And also, if SSL handshake hasn't happened, if you try to call the wrap or unwrap method, they might also trigger the TLS handshake. As we already said, it's much more complex to use than the SSL socket API. It's typically used along with another not so well-known API called socket channel. However, one thing that's important for you to know when you use either the blocking or non-blocking mode of operation is how you can debug SSL messages that are flowing between your endpoints. And there is one very useful property you can use. It's called javax.net.debug. By specifying this property, you can inspect what are the raw SSL messages that are exchanged between the client and the server. And this property is customizable. You can inspect only messages that are exchanged during the handshake process by specifying the handshake value. Or you can specify only that you want to see only messages that are exchanged when the actual handshake has happened. And that's if you specify the SSL value. And of course, you can combine those two values by specifying the old property, where you can inspect all of the traffic that's flowing between the endpoints. So that's in short about the state of TLS before JDK 9. Now, considering that in JDK 9 we have something new introduced which is called DTLS. DTLS basically is TLS over an unreliable communication protocol such as UDP. In many scenarios, many applications that need to establish secure communication between themselves are not running on top of a reliable protocol such as TCP, but they're running on top of UDP. And examples of such applications include applications that make use of the DNS protocol or chat servers that use the SIP protocol and many others. Any type of, for example, gaming server that's written in Java may also run on top of UDP. And DTLS basically bridges the gap between TLS and UDP by providing support of TLS over UDP. And another interesting thing behind DTLS is that it follows closely the TLS version specification versions. So the latest one is version 1.3, which will eventually be supported at some point in the JDK. But for now, the JDK basically supports version 1.2 of the DTLS protocol specification. And there are several differences between DTLS and TLS. Most of those differences are related to the fact that DTLS runs over UDP and not over TCP. So one of them is that in DTLS you have a new field added to the protocol message, which is called sequence number, explicit sequence number. As you know, in UDP, the order of packets that is delivered between the parties is not guaranteed, so you need to have some way on the application side to reorder messages. And for that reason, you have the sequence number field added to DTLS. Another difference is that for DTLS, there is some support for cryptographic chiffres dropped. And if you go to the Oracle documentation, you may see which of those cryptographic chiffres that are supported by TLS are not supported by DTLS. Also, there is another field added, which is called retransmission timer. And as you might guess, retransmission timer is used to allow you basically to retransmit messages that have failed over the network. This is something that in TLS you already have it because it runs on top of TCP. And there are two other more minor differences. One is that MAC verification failure triggers warning instead of failure in DTLS. And we have a new request message added to the DTLS protocol, which allows you to identify additionally the sender of the message. So if you want to use DTLS before Java 9, you had several options. One of them is to use an implementation provided by a third-party security provider, such as the Bouncy Castle library. And the Bouncy Castle library has a provider for JSSE, which is called a Bouncy Castle JSSE provider. It has an implementation of DTLS that you can use with earlier versions of the JDK platform. Or another way you can interact with DTLS is by using some JNI bindings and interact with libraries such as OpenSSL, which also provide implementation for DTLS. And one of the things about DTLS is that the implementation is adapted to the existing JSSE API. You won't see any new paradigms introduced with the implementation of the DTLS protocol. And one of the things is that the more complex mode of operation in JSSE, or the non-blocking mode of operation, is chosen for the implementation of DTLS in JDK 9. This makes usage of DTLS out of the box quite complex, because as we already mentioned, the SSL Engine API is not so well known to the Java community, is not so widely used and adopted. And in my opinion, if you want to use DTLS in JDK 9, you would still better go with a third-party implementation like the one provided by the Bouncy Castle library. So one of the specific things about the DTLS implementation in JDK 9 is that order delivery is provided automatically during the TLS handshake process. You can imagine that if TLS handshake needs to happen, you cannot afford to have unordered delivery of messages, or you cannot afford to have failed messages during the TLS handshake process. And for that reason, the DTLS implementation in JDK 9 makes sure behind the scenes that those two things happen in the TLS handshake. However, if you want to use DTLS in your application, you need to make sure in your application that you redeliver messages properly if they have failed for some reason. Or you need to also make sure that you order messages properly. And for that reason, there is also a new method added to the SSL Engine result class, which is called sequence number, that allows you to get the current sequence number of the message that you get from DTLS. So in order to get started using DTLS in JDK 9, the first point is to get an instance of the so-called SSL context, which corresponds to the DTLS implementation. Then you initialize that SSL context with some additional security information, such as the key store that's used by the SSL engine, the trust store, some additional security parameters. Then you create an SSL engine using that SSL context. You specify whether that SSL engine corresponds to an SSL client or server. And at that point, you can start exchanging messages between the client and the server using the wrap and unwrap methods, which are provided by the SSL Engine API. And there are some good examples provided by the JDK 9 test suite. If you go to the OpenJDK source code, there are a set of a few unit tests that provide a clear example of how you can get started with DTLS. At that point, there is no good documentation available for DTLS in the official Oracle documentation. And in my opinion, further releases of the Java platform need to simplify that API for developers like us. At that point, as I would suggest, just go and see the unit tests in the OpenJDK source repository. Another much simpler to understand and use extension of the TLS support in JDK 9 is the so-called TLS ALPN extension, or Application Layer Protocol Negotiation extension. And the main thing about the ALPN extension is that it can be used to identify the application protocol that's negotiated between the client and the server. Originally, if you establish SSL communication between the client and the server, you know on top of which application protocol you want to establish that communication. That could be XMPP, that could be DNS, and so on and so forth. But now with this extension, basically, during the TLS handshake process, you might determine what is the application protocol that you need to establish. And one thing in addition to that is now that the SSL server may send different public certificates to clients based on what application protocol is negotiated between the parties. And one very good use of this is if, for example, a server supports different versions of the HTTP protocol. Now, you know that recently a lot of people spoke about the upcoming HTTP 2.0 version of the HTTP protocol. And now many web servers start enabling HTTP 2.0 support. And basically, if you have some clients that work only with HTTP 1.1 and new clients that support HTTP 2.0, you may negotiate SSL communication between those parties in a different way using the ALPN protocol. Basically, newer clients may use one public certificate and older clients may use a different public certificate that's provided by the TLS server. And how you can use ALPN in your application? From the SSL socket instance that you use to establish SSL communication, you get an instance of the SSL parameters class, which stores some security information over the SSL socket. And you call the set application protocols method, which accepts just an array of strings that identify the application protocols that are supported by either the client or the server. And you can do that both with the blocking and non-blocking mode of operation of SSL. After this happens, the TLS handshake process is triggered in some way by you either calling explicitly the start handshake or begin handshake method, or by trying to read or write to the socket or the SSL engine, depending on which one of those you use. And after the TLS handshake process finishes, you can get the negotiated application protocol by calling the get application protocol method on the SSL socket or SSL engine instance. And it's a very simple way to negotiate the application protocol between the client and the server. However, if you want to provide some more complex logic to negotiate the application protocol, you can call this, the set handshake application protocol selector method over the SSL socket. And that method basically accepts a lambda with two parameters. First is the SSL server socket, and the second one is the list of the proposed client protocols. This basically lambda is called during the TLS handshake process to determine which is the application protocol that you need to use. And in that particular example, I get the current SSL session. And from that session, I get what is the negotiated cryptographic cipher between the client and the server. Then I get the negotiated packet buffer size, which is 1024 bytes. And if the negotiated cipher is RC4 and the packet size is bigger than 1024 bytes, I return protocol 1 as the application protocol. Otherwise, I return protocol 2. As you can see, this is a much more customizable and complex way to negotiate the application protocol during the TLS handshake process. Now, to see how these things work in practice, I'll be using a demo scenario. I'll have a very simple banking application server. And my banking application server, you might imagine, that provides support for different application protocols. Let's say that in the bank, there are different applications that work through the XMPP protocol or the SIP protocol. And also in that banking server, I may deploy different applications that interact with the various third-party services in the bank. Now, at that point, I'll switch to my Eclipse environment. The first thing, basically, before we show the examples of how these APIs work, is to note that all of our protocol implementations and the banking server are packaged as Jigsaw modules. This is the Jigsaw metadata of my banking application server. It requires the Java logging module from the JDK. It's the only module it requires. It exports some packages that might be used by other protocols and applications. And it provides two services that might be implemented by other applications. One of them is the application protocol service, and the other one is the banking application service. As I already mentioned, this has an implication in terms of security. You can see that we have 4 packets from the banking server which are visible to other modules. And this sandboxing model, in a way, improves the security of our application when we define it like this in the module info.java file. Another thing is that if I run basically that banking server using a stripped down version of the JDK, you can try this out by using the JLink tool and building a custom JDK image. And then you can specify that JDK image in your ID of preference. This further also improves the security of your application. So The banking server is fairly simple. We use something called the service loader utility, which is one of the utilities behind the module system in Jigsaw that allows you to retrieve implementations of different services from the module registry. And using the service loader utility, I get all implementations of the banking application service, which needs to be implemented by all banking applications. And using those applications, I call the execute method to execute the logic of each of those applications. Also, we have different implementations of banking protocols in that server. For example, if I'm look into the fixed protocol implementation, this is one sample application protocol. It basically implements the banking protocol service which comes from the banking server. It's provided as a Jigsaw service. And it has a name which is called fix, fairly simple, and some logic that allows you to execute a raw packet over the network to some application. In that particular case, I don't care what's the structure of the packet and so on. If I'm to see how this works in practice, basically I've already built the banking application server and I want to compile my demo application. The way I do this is by using the JavaC utility and specifying the so-called module path that basically contains already built all of the modules of my banking server. This includes the various protocol implementations, the banking server itself, and so on and so forth. So I'm going to build my demo application, and if I'm going to execute that demo application, I can see that basically it sends some message over the fixed protocol over to the network. So let's see how this demo application works. It's fairly straightforward. It basically creates some raw packet that needs to be sent over to the network. It gets a protocol service provided by the banking application server. And using that protocol service, it sends a packet over to the fixed protocol with the information in the packet. This string here, fix, is determined using the service loader utility based on the information provided by the fixed protocol implementation. That's in particular here, this string. Now, imagine that in this scenario, we have some third-party application in the bank, let's say some chat application that communicates over the XMPP protocol. For that reason, I'll simulate my chat application by using a very simple SSL socket server that supports XMPP version 1.1 and XMPP version 1.2 of the protocol. The essential thing here is the set application protocols method that I call. This logic that you see here, this piece of code, is the same that we saw earlier on the slides, the one that we used to create the SSL socket, the SSL server. And the only additional thing here is the calling of the set application protocols method, which specifies which are the application protocols supported by the SSL server. In that particular case, this is our chat server in the bank. So I'm going to run this. And on the other side, I also have an implementation of an XMPP client, which is used to communicate with that XMPP server. The XMPP client is also fairly straightforward. It has the same implementation as the one which we saw on the slides for the simple SSL client, with the addition of the set application protocols method call, which specifies that our client supports only version 1.1 of the XMPP protocol. Now, if I'm to go to my demo application and change the application protocol that I would like to use, in that particular case, XMPP, and I recompile my Jigsaw module and run it again, I can see that version 1.1 of the XMPP protocol is negotiated. And this is the minimal, this is the first version of the XMPP protocol that's in common between the client and the server. I might have the scenario where the client and the server support at the same time multiple versions of the same protocol or multiple different application protocols. The first one that's negotiated between the client and the server is typically the first one which is in the list of protocols that resides either on the client or the server. And now imagine that we have yet another scenario. In the bank, we have some other chat server that works over the SIP protocol. And basically, in order to establish secure communication between that chat server and my banking application, I need to use basically the DTLS protocol, which runs over UDP. In order to look how such a chat server would look like, I have an implementation provided by the DTLS server class. That implementation is fairly complex because it considers a lot of side cases that need to be handled by your application during the TLS handshake process. This particular example is derived from the OpenJDK test suite. I'll not go into the gory details of all of the things that happen here, but the essential thing to look into is how is the SSL engine instance created. The SSL engine instance is created by the create SSL engine instance class. Here we get an instance of SSL context for DTLS. Then I create the SSL engine instance. Here I don't specify any additional parameters. I specify some additional parameters such as the maximum packet size. And at the end I specify that this is a DTLS server by calling the set use client mode method and specifying it to false. And that's pretty much it. Now, if I'm to look how is a DTLS client implemented on the other side, this is some protocol implementation in my banking server, which is provided by the SIP protocol implementation. And my SIP protocol implementation also is fairly complex because it also needs to take into account pretty much the same stuff during the TLS handshake process as my SSL server. But again, here the essential thing is to look into how the SSL engine instance is created. It's pretty much similar as how the SSL server is created, with the difference that here I specify that I'm using SSL client rather than server by calling the set use client mode and specifying true as a parameter. Now, if I'm to go back to my demo application and specify the SIP protocol, which I want to use with my demo application, I'll again recompile my demo application Jigsaw module. I'll run it. And here some DTLS communication kicks in. In this particular example, we won't see any communication flowing between the client and the server because it's a non-blocking mode of operation. It needs some good synchronization between the client and the server. But in general, you get the idea of how you can establish DTLS communication. So going back to the slides. Now, this was pretty much, in general, the main features provided by JDK 9 in terms of the TLS support it provides. However, we have a few other interesting security enhancements. One of them is the so-called OCSP Stapling for TCP. OCSP, as we mentioned earlier, is a protocol that allows the client to do certificate validation checking against the certificate authority. And what the client does is basically takes the public certificate from the server. It uses the OCSP protocol to send a request to the certificate authority and get a response which identifies whether that public certificate is valid or not for some reason. However, this might be very overwhelming for the certificate authority because it gets a lot of requests from clients. And for that reason, OCSP Stapling provides an optimization technique that allows the SSL server to do that call. And when the SSL server does that call, it may also additionally cache it, so that it reuses it and does not send multiple requests to the certificate authority. And in order to enable that optimization technique for TCP, you need to specify several properties on the client, on the SSL client and SSL server. On the left side, you can see we need to specify two properties for the SSL client. One is enable status request extension equals true, and pretty much a similar property for the server. And for the client, we also need one additional property, which is check revocation equals true. These are the only things that you need to specify in order to enable OCSP Stapling. Also, as we mentioned, we have PKCS12 Keystores by default. Before Java 9, we had a proprietary format called Java Keystore, which was, however, not very interoperable with other applications written in non-Java language like C#, Python, and so on. However, in JDK 9, the PKCS12 format was introduced by default. And the PKCS12 format is derived on the basis of a very mature specification that defines this format. And another benefit from using that format for the keystores is that it also supports storing certificates that are generated using stronger cryptographic algorithms than the ones that are supported by JKS. So it's a benefit for the Java platform that now we have a much more interoperable format for key stores that's provided by default. And a few other enhancements. One is a new implementation of secure random, which is used to generate cryptographically strong random numbers used for various cryptographic operations in the JDK. We have also some performance optimization of the Ghash and RSA cryptographic algorithms, which is achieved through CPU instructions, which are now supported by the JDK. We also have support for SHA-1 certificates disabled in the Java platform, meaning that if you have some public certificates which make use of the SHA-1 series of algorithms, in JDK 9 you will no longer be able to use those public certificates. And also we have an additional implementation of the SHA-3 series of hash algorithms in JDK 9. These seem like minor changes, but really a lot of work has been done behind the scenes to achieve those. So I would say this is quite some stuff that's been added to the Java platform. And as a summary, JDK 9 introduces a significant set of enhancements, in particular to the TLS protocol that's supported in the Java platform. We would expect that in further versions of the JDK, we would see many new enhancements in regard to the 1.3 version of the TLS specification. Also, we would hopefully see further that the platform provides much more solutions for security vulnerabilities that are open at the moment. And one new thing that we might see now in JDK 10, for example, is that Oracle has exported its set of trusted certificate authorities to the C8 file. This is something that wasn't present before in OpenJDK 9, but as of Java 10 it would be available. So that's pretty much it. Thank you for attention. And we have 3 more minutes for any questions. Anything related to security in Java? Yep.
Two questions. The first one I guess it goes on the JDK 9, and is it backport to JDK 8 since it's a TLS, or sometime with specific issues? Some of them, for instance,
So the enhancements that we saw, DTLS and ALPN, they are fully backward compatible. So they are new additions on top of the existing JSSE API. They are just further implementations. However, some of the other stuff that we saw are really not that backward compatible, such as, for example, the SHA-1, the dropped support for SHA-1 certificates. If you use them in your application, that would eventually break if you switch to JDK 9. But for the most part, most of those stuff are really backward compatible.
Okay, so I go again. You talk about Bouncy Castle, and so I'm sorry for I might be wrong with the name, but basically you load it with the extension system before the JDK 9. I think with the module compilation, this loading function change. Am I correct, first of all? And then what would be the extent, especially when you try to build module with the Bouncy Castle, for instance?
So your question is basically if you want to load Bouncy Castle in JDK 9, would that work out of the box directly?
Yeah, especially with the module issue.
Well, if you know that in JDK 9, basically we have a mode that allows you to switch back to eventually a compatibility mode with older versions of JDK. So if you use that compatibility mode, that allows you to use the JDK without any modules, you will be able to easily use Bouncy Castle as it is. I haven't tried to use it in JDK 9 without compatibility mode, so I'm not sure if you might get into some issue with that, depending on probably also what libraries does Bouncy Castle use. For example, whether it makes use of the unsafe API. If it uses unsafe, well, you won't be able to run it directly in JDK 9. Thank you. Okay, any other questions? If no, then thank you once again, and yeah. Enjoy the rest of the conference.